So we'll have like these review questions for both of the data passes and the cache memory. We'll begin with this review question that compare two pipeline implementations, options A and B, with 4 and 7 stages respectively. The logic delay of the pipeline stages are follows. I'm giving you stage 1 this, stage 2 this, stage 3 this, stage 4 this. This is for option A. For option B, you have these other values. As you can see from here, it's not as usual the number of stages like 5 as we had earlier. One is less, one is more. So the first question is, what are the maximum clock rates for the two implementations? So if I were to think about that, so now I have a pipeline, I need to design my pipeline, correct? If I would like to design my pipeline, I have to have a clock. So what I'm asking you here, what is the period or the frequency, which will be 1/t of that particular clock? So how we should think about something like that? Basically, as we have described earlier, we can see which one will be the slowest in all of these stages. So I have 250 for option A. 250 picoseconds, 180, 400, 200 picoseconds for each of these stages. Which one of these had the most consuming time? You will find that this 400 picosecond is the most consuming time, correct? Which gives us an indication that if we plan or if we have our clock that satisfies the lowest, of course it will be able to satisfy the fastest. You can't go the other way around. If you go the other way around, unfortunately, you won't be able to satisfy any other thing that is more slower than that particular clock. And because of that, the clock rate will be basically depending on this value, which will be just 1/t. So you have the t, it will be just 1/t. How about for option B? Same concept. We have 200, 150, 250, 250, 200, 150, 180. Which one is the maximum? You'll find that we have here the 250. So basically, the clock rate will be 1/250. I'm expecting also that you will be familiar with the pico, nano, gig, and so on and so forth. So what exactly that means, and so on. So for option A, it will be just 1/400 picosecond, which is also 0.4 nanoseconds, by the way. You can do the math and you'll find that this is same, it's 2.5 gigahertz. For option B, it's 1/250 picoseconds. Will give you 4 gigahertz. So even though I'm assuming that this is very trivial, from my previous experience, that I found that some of the students have not been able to get that correct. Let's move forward. So the table below states the operation of each pipeline stage, option A and option B. Option A is just 4 stages, option B, 7 stages. So this is compared to the MIPS CPU, which we have actually covered through the semester. Option A merged the instruction fetch and the instruction decoding in a single stage, as you can see here, while option B splits EXE over 3 pipeline stages, EX1, 2, 3. Registers and memory are written to in the first half of the cycle and read during the second half of the cycle. So it's the same concept as exactly what we have covered in MIPS regarding this issue. There is no forwarding path. So the question is, how many instructions are executed after an add and load word instruction, respectively, before the new register values are available? So if you have, as an example, option A, and you have an add. Okay, so you have here IF, ID, and then you have execution, and then you have memory, and then you have write back, correct? This is what we have from here. Is that correct? When exactly the results will be available in this ad? There is no forwarding. As we have mentioned, there is no forwarding. We expect that this will happen here at this stage, correct? At the write back. Yes? So this gives us an indication that I will not be able to decode the following instruction unless I have this value here. Correct? So I have to align the ID stage with the write back. Since also in the question it is mentioned that we can write and read in the same clock cycle. If I said you cannot do that, then you have actually to switch to the next cycle. But since I said that you can do that, so what I need to do is just align the ID with the write back. And since the IF/ID are in the same exactly stage, so I will align the IF/ID with this guy, and then just like the same things exactly here. How many stalls do I need here? 2, yes? 2 stalls. So basically with option A, I will have 2 stalls if I have an AND. Let's think about option B right now. IF, ID, EX1, EX2, EX3, memory, write back. When the AND will get the results again at the write back, what I need to do is with the same exact concept, I have to align the ID with the write back, because actually this is the same register. I'm writing back to the register. The instruction, the coding is actually in the same register, so I need to align both of them. And since I can write and read in the same clock cycle, so what I need is just aligning this ID here. If I am aligning this ID here with the write back, so instruction fetch will be here, and here just like continue. If I'm asking you like how many stalls do I need in this case? 4. So with this option B, with the AND, I will have 4 stalls. But all of this, since I mentioned that I can read and write in the same clock cycle. If I said, no, you cannot do that, in this case, actually, this ID will have to shift one more clock cycle after the write back, because you will write in the previous one, and then you will read in the following one. The same will happen with this guy. Okay, so it will change from, instead of 2.4, it will change to 3.5. How about the load word? It's exactly the same. Yes, because the load word also will have the data at the write back, and you will guess exactly the same thing, so it will be also 2 and 4, as you can see from this table. So what I showed just earlier, that I went through this step by step, so I am sure that you do understand how we did get these values. So if I'm asking you calculate the number of instructions executed per second for each implementation for the specified FS or sampling frequency, there are not necessarily the correct result for part 1. So for option A, I'm giving you FS and CPI. I'm telling you that doesn't have this one is correct with the one that we have calculated. I'm just giving you any number to show like a value that you need to use in order to calculate my request. And I'm giving you the CPI. And I'm asking you to calculate basically the number of instructions per second. This is my question, correct? An instruction executed per second. So if you go and review all of the equations that we had with chapter 1, you will just like be a direct substitution for here in this question. It's exactly the same as we have covered earlier. However, even if for some reason that you feel that no, I can't remember all of these kind of things, this is very, very trivial for you to know exactly what you need to use with these 2 values in order to get the correct results. I'm asking you to get instructions per second. correct? This is what I'm asking you to get. I'm giving you the sampling frequency, and I'm giving you cycles per instruction. So I'm giving you cycles per instruction. And I'm giving you the frequency. What is frequency? Frequency is basically how many cycles per second, correct? If I'm giving you these and I'm asking you to get that, how you will be able to do that? With units. If you do instructions per cycle, cycles, multiplied by cycles per second, cycles will go with cycles and you will get instructions per second, correct? Cycles per second is just the FS, correct? What is this? What is CPI? Cycle per instructions, yes? But this is instructions per second, so it's actually the other way around. So just 1 over CPI. So if I do 1 over CPI multiplied by FS will give me that, correct? Just by the units. I'm just giving you like the worst case scenario in case like for some reason you just forgot the things. You have just like to make your mind work and you should be able to solve. Going to the next question. So I'm giving you a cache memory. You can tell, of course, since like we have the blocks and the tag, that this will be n associative. It's not like a direct map. I am giving you here all of the addresses needed for the tag, for the index, for any other thing. Also, I'm showing you here that with this multiplexer, you have 1, 2, 3, 4 inputs. It shows you like there are like 4 of these, correct? And we have the tag in order to choose either this or that and so on, so forth. And then we will begin to ask some more questions. With this, even 32 bytes, we'll have like another 3 here to choose like exactly from this which byte address is this one. So giving all of these things, we are asking you some questions. What is the block size of the cache in bytes? What is the block size of the cache in bytes? What is the block size of the cache in byte? So the block size of the cache is just 32 as shown directly from the figure. The next question is, what is the number of blocks in this cache? What is the number of blocks in this cache? So basically, the number of blocks, so we have from bits 5 to bits 10. So actually we have for the indexing 6 bits. So we have, you can think of this as 2 to the power of 6 rows, yes? And then in each row we have actually 4 blocks. So it will be 2 to the power of 6 multiplied by 4. It will give you this number of blocks. As you can see from here, this index, it shows you like how many floors, correct? You can think of it that way. As I mentioned again, if you actually thought the other way around, you don't have actually to multiply by 4 in that case, correct? With the other way as we mentioned. So what is the total data capacity of the cache in bytes? What is the total data capacity of cache in bytes? So with this total number we have from these 256 blocks, but the capacity we have like 32 bytes for each, so we have actually all of these number of bytes. How about what is the total number of valid bits in the cache? What is the total number of valid bits in the cache? So this will be basically the same amount as we had earlier for the blocks, because each block actually had the validity bits. What is the total number of tag bits in the cache? So if we would like to think about that, we have to know exactly what is the number of tag bits. So the tag size multiplied by all of the total number of the tags, correct? So you can say that this will be 256 because this is the total number, and then multiply it by the tag size, which is from 11 to 31. You count that, you'll find that this is 21. So this will be 21 multiplied by 256. It will give you that number.